Demonstrate how a transportation problem can be transformed into a linear programming problem and solved using Python. Because usually transportation problems are very large and they cannot be solved using Excel. And in such cases, we have to use programs like Python, and that is what I will be demonstrating in this lecture. Transportation problems. So normally transportation problems, when they are used practically, can be much larger in size. And therefore, solving it in Excel would become very difficult, and one may have to use programs like Python, R, and LP-Solve IDE to solve it. So I'm going to today demonstrate how a transportation problem can be reformulated as a linear programming problem, particularly when the number of variables exceed 30. I'll just demonstrate how these equations are made. I've kept the problem small so that you understand how the problem is to be formulated, and then I will show you how a bigger problem is solved using Python. So in a problem like this, now assuming you have about 10 supply sources and about 8 plants, then you're roughly talking about 80 variables. You're talking about 80 variables, so that's not possible in Excel. So if this problem has to be, I'll just formulate. So we have to, when the problems become large, you have to solve it in a software like R, Python, LP Solve IDE. Now I'm going to now demonstrate how this transportation problem can be converted into a minimization linear programming problem and then solved. So carefully look at this transportation matrix. These are the transportation costs, which we are going to minimize. So our objective function would be 4x11 plus 7x12 plus 5x13 plus 7x14 plus 6x21 plus 3x22 plus 4x23 plus 2x24 plus 3x31 plus 4x32 plus 5 plus 6x33 plus 4x34. Right? So that's going to be our objective function. So you can just about see it over here. So I've converted that objective function into one row. So this becomes a minimization. The objective function becomes 4757, 63, so on and 4 till 4. So this is my objective function. So when I run a transportation problem as a linear programming problem, all the cost coefficients should be taken into the objective function and then converted into an objective function. And the constraints are basically this. That means plant 1, the quantity that it receives from A, B, C, and D should not exceed 100. Plant 2, what it receives from A, B, C, and D should not exceed 120. And plant 3, which it receives from A, B, C, and D should not exceed 150. Similarly, second constraint is the amount of supplies that A gives to plant A gives to plant B, and A gives to plant 3 should not exceed the total supply of A. Similarly for B. So these constraints have been formulated, and that is what we have done over here. So what you're saying is this row. So this, and this should be less than or equal to 100. So I say 1, 1, 1, 1, 1, because variables have different names. Okay, each cell has a different variable name, and that is why it cannot be put in one row. So when you come to the second row has to add up to 1. Have to add up to 120. The third row has to add up to 150. Now here we get the columns. So the first column, the second column, the third column, the fourth column. So first column, the second column, the third column should add up to 100, meaning this. So it has to be shown because this is x11, this is x21 and x31. x11, x21 and x31. Similarly, next will be x12, x22, x32. Should be less than or equal to 100. Should be less than or equal to 100. Then the last column should be the last column should add up to 100. So now this is a formulation of a linear programming problem. This is a formulation of a transportation problem as a linear programming problem. So this is how it's done. So this has to be very carefully done, and then it has to be formulated. Now I'm going to now show you a big problem. Rather than showing you a small problem and then solving it, I'll show you a big problem where we've got all the now this is just like a transportation problem. We have here, you can see there are many processing plants, and this is the production centers. Each province has a total amount of production that produces so much. This is the transportation cost, and this is the demand, a very big problem. This is the demand. This is the demand of processing plant 2, 3, 4, 5, 6, 7, 8. Yeah, doubly there are 14. So since unbalanced, the total capacity of these plants the total capacity of these plants is equal to 1,09,036, and the total availability of the raw material is much more than that. It's much more than that. Okay. It's much more than that. The total capacity is 2,926. The total production is 10,000. The total consumption is 2,900. The total production is 10,000. So the difference between supply and demand is 8,099. So I created dummy row because demand is less, whichever is the shorter side. Demand is less. So for demand, I created dummy row. Give the value 8009.868. And now it is a balanced transportation problem. You can see the difference is equal to 0. So I've transported. So now do you see, this becomes my objective function. So just to recall what I showed you earlier. Now this entire thing should go into the objective function. So you can imagine how big it's going to be. So just about imagine. So you're going to roughly have 450 variables. How do I get 450 variables? I have how many rows? 1, 2, 3, 4, including my dummy, I have 15 rows. So 15 into how many columns? The total columns is 30. So 15 into 30 makes it 450 variables. I will have 450 variables. Okay, so 450 variables I'll have. So I have to convert this just like I did over there. I have to convert it into one row running from 1 to 450. Let's just show you that. I've created that. I called it objective. So what I did is I read the whole thing and put it into one single row from A down to QH. If you want to know what is the column number here, you just say column. I'm not solving it in Excel. I'm just going to formulating. So the 450, just the same thing what I showed you over here. Just the same thing. And now convert it into. Now I'm going to create this. So these I call as input-output coefficients in linear programming, and these are the constraints, and this is the inequality. Yeah. So please remember, whenever you do linear programming in Python, all the greater than constraints should be put together. All the less than constraints should be put together. You cannot mix it up. You can formulate it in any way you want. Then you can sort it out so that all the inequalities are in the same direction. Now, for instance, here you have 1, 2, 3. 3 greater than and 4 less than. They should all be together. The same thing I follow over there. Now, this is the objective function. Now I'll split this into two. I'll make one file with only greater than constraint and another file with only less than constraints. Okay, so that's what I've done. So you can just see, because this is what you'll do when you work in R. So that's my objective function. This is my A matrix. I showed you there. The first part, 1, 1, 1, 1, 1. You would have seen that. 1, 1, 1, 1, then 1, 1, 1, 1, 1. Same. That's the first part of the constraints. So since I've got a very, very big data set, this also goes in the same number of columns which you have to check. This should also have 450. Otherwise, you made a mistake. So you say equal to column. Open and close the bracket, 450. So this is also fine. Then I'm going to take another matrix with all the less than or equal to. Okay, this is A1. This I call A1. This I'm going to call A2. What is A2? This part, where the constraints are all less than. So create another matrix which one. Then this A2 is the one which will have a diagonal kind of matrix. You can just see that. Like it'll go step by step. Look, it comes step by step. Same way as you got over here. And you have an inequality and inequality constraint. Okay, so this I've created A2. Then I'll put the constraint values. Constraint values are these. It is either demand or the supply. In this case, it is a demand. Okay. So the same way, I'll put the constraint values here also. I've got another matrix for constraints. So each one has to be created as a separate file. So 620, I'll show you. 620, yeah. 620, 73, yeah. Similarly, I'll create this also as a constraint call. So that's constraint 1, and this is constraint 2. What is constraint 2? Come to the formulation, the supply. 418.9. Oh, so 489.9. 489.9, sorry. Constraint 2 starts with 489.9. So basically, you formulate a linear programming, break it up into its various components, and then you go for solution. So now let's see, I've got an objective function, I've got an A matrix, I've got an A2 matrix, which has a different set of constraints. I set the first set of constraints, and I'm going to set a second set of constraints. And now I'm going to solve it in Python. Because the problem is very, very large. It cannot be handled in Excel. So now I'm going to solve it in Python. Okay, so I have opened Python, and I have opened the Jupyter notebook. And I'm going straight into the solution without getting into the basics of Python. I'm going straight into the analysis. Now, to run linear programming, one of the packages available in Python is CVXPY. So just like we normally do, and if that file is not there, then you have to install it using pip install CVXPY. You get this information from the net. So you put a hash and then you run it. And then the conventional, what we normally do is we import an operating system, we import NumPy as NP, we import pandas as PD, and we also import CVXPY, which is just installed as CP. These are their aliases, and these are the essential files that we're going to use for calculating. Okay, I don't require this because I've already installed. So I'll just run it with Shift Enter. The star is there, so that means the program is, these packages are being loaded. And once a package is loaded, then I set my folder. I say I'm waiting in a folder called to 2022. So I'm giving the path and I say os.change directory, chdir, and I do that. So that my file, which I'm going to use, that file that I just showed you, the file that I've used here is the one that I'm using here. It's called KMF Milk Unions for LP New. Okay, that is here in this program. That is there in that file. Okay, so this is what I am going to do. So I'm going to now set up the sheet. So that file has got many sheets. I'm not interested in all the sheets. Like as you may see, that particular file has many sheets. It has many sheets. It has an objective function sheet. It's got an A matrix, A2 matrix, constraint 1, and constraint 2. So I would want only the ones, and I'm very particular, the name should be correct. There should be no spelling mistakes, otherwise the problem runs. So what I do is I run one step. I try to identify what are the sheets in the file. And for that, I create a file called sheets, and I create a file called sheets. Right? And then pd.excel file. In this file, KMF milk unions for LP new.xls. In Python, you also require this extra command. Engine is equal to open pyxl, which is not required in the Windows version. This is required only in the Mac version. So now I'm going to read the sheets with this file pd.excel file. Open a bracket and say KMF milk unit. That's the name of my file, and I just run it. And then I get the names of the sheets in this file called KMF. I call it sheets.sheet_names. And it gives me the names. So I'm interested only in this objective function, A1 matrix, A2 matrix, constraint 1, constraint 2. I'm interested only in that. So I'm now going to read them one at a time. So first I'm going to create the objective function. Objective function is what I created here, like this. Objective function in this case would be this sheet, this one, with all the data, with all the coefficients of the objective function, no variable names. Okay. So I'm going to create an objective function. I'll read it, pd dot read underscore excel, because it's an Excel file, and I give the file name. Engine is equal to open py excel is required in for Windows for Mac. Sheet name objective function. This is very important. Header is equal to none. If I don't say header is equal to none, it will take the first line as the header, and that's going to create a lot of problems for estimation. So it should be only the data, and the data should be the first row. Okay, and there are no column titles here. So this should be very careful. So that's why I put header is equal to 1. I'll run it. So this is very important. Okay. So this is very important, because if you don't do this, it'll read the first line, because there's only one line of data. That one line of data will become the column titles. So if I put header is equal to none, I will get only the number, as you can see now. So I've run it. I must convert it into an array. To solve linear programming problems in Python, you need to convert it into an array. So I create it as objective function. No, it's called objective. I couldn't get the name. Yeah, it's called objective function. I'm going to convert it into an array. That it means it will not have any title. It'll have rows, like a matrix. I'll say objective function np.array, the same variable. So now you'll see. And if I ask for the shape, it says it's got one row and it's got 450 columns, which is what we want. Then I'm reading the A matrix. Please see what I did. The A matrix, the input-output matrix. First one I'm going to read. Right? First one also I'm going to read. So I say A matrix, PDXL, open Excel, sheet name, A1 matrix, header is equal to none. And I straight away here itself, I convert it into an array. Like I say np.array A1. So it gets converted into an array. And if I want to see what that array looks like, there it is. So it's got those 111s and the last row 111s. Then I'm going to read A2, which is the second part of the matrix, A2, which has got all the diagonal element ones, which adds up the column. And then this also I convert it into np.array. And then when I look at A2, then you'll notice it's a step 1111. The same way what we got over here. Same way like we got over here. Let's go to that step. Okay. Okay, so now we got it. Now the constraints. The constraints are in a file. You see, I've shown you the constraints. Constraint 1, it has got 15 rows. Constraint 2, which has got 30 rows, as you can see, right? So here I say constraint read open Excel, sheet name is equal to constraint 1, header is equal to none, and I convert it into an array with using the command np array. And then if you want to see what it looks like, there it is. Right? There are the constraints. The first value is 620. So in constraint 1, the first value is 620, last value is 8009. Okay. Then we do constraint 2 in the same way. So pd underscore excel read engine open. Sheet name is equal to constraint 2, header is equal to none. And constraint 2 is equal to np.array. I convert it into a constraint 2 into an array. And if you want to look at it, this is what look. The first value is 489. Constraint 2, the first value is 489, and so on and so forth. So now we have set up the problem. The problem is very easy, except that you have to break it up into parts, read it up separately, and see that they are compatible. Now I'm going to create the X variable. I'm not sure whether you can create the X variable yourself and read it as an X. If you have not done it, I mean, you must experiment with that. Or alternatively, I can say X, I'll define the X variable as cp.variable. Now you may notice in Python, the CP you're referring to this CVXPY. So that's what's doing that step. So I say cp.variable shape is equal to, so I want variable is 450 column, because it have to be compatible. No, I'll have to multiply the objective function with X. So X should be a column vector. Objective function will be a row vector, because we said no, objective coefficient is a row vector. The When you want to multiply, it should be a column vector. Let me just show you that. Look, when you took the objective function, it's a row vector. No? So to get an objective value, you must multiply this by x1, x2, x3, x4, and 50. So it should be a column vector. So what I'm telling the computer is, create a shape should be 450 rows, one column, the name should be x. So you can just see that. And then when it creates the x variable, it says 450 into 1. It's created that. Okay. Then I want to see whether they are compatible. I'm seeing input-output coefficient matrix 1 and input-output coefficient matrix 2, which one is for greater and the other one is for less. I say that, yeah, one is 15 rows and 450 columns. The other one is 30 rows and 450 columns. So no problem, they're constrained. Now I'm going to set up the constraint. This is important. This is a very important step. Now, in a linear programming, you know there are constraints. There's an objective function, which we have already defined. There are constraints which are matched with the input-output coefficient, which are matched with the input-output coefficients. Okay, now please see this. So I'm now defining the constraints. CP is, of course, the program that we're using. Dot matmul, matrix multiplication, matmul. A1 is the input-output coefficients. A1 is the input-output coefficients, which I showed you over here. This one. Multiplied by x. Multiplied by x, the same x that we created over here. You can see this. So this will be 30 into 450 into 450 into 1. So it's compatible. And these are all the greater than equal to constraints. So I told you, you have to divide the constraints into two sets. So the matrix into two sets. One which relates to less than, and the other one that relates to greater than. Same thing I'm going to specify over here. Please see constraints matmul a1 into x. These are all greater than constraint 1. Then cp.matmul a2 into x less than constraint 2. And this condition that all x's should be greater than 0. That's a linear programming constraint. I run it. And if I want to just see what it is, it just defines broadly what it is. So it's got 15 rows, one column. This has got 30 rows, one column, and then the whole thing is the same. Now, I want to now bring the objective function. Now, in the objective function, the objective function coefficient should be multiplied by x. And that is done over here. I just want to see whether the shapes are compatible. And I say yes. So it'll be a 1 into 450 into 450 into 1. The result will be 1, and that is your objective function value. That is it. Now we are ready to solve. We say objective is equal to cp dot minimize. If it's maximize, you should say maximize. Open a bracket, cp matmul objective function into x. Objective function into x. That's my objective function. My constraint is, now I'm going to specify the problem. The problem should have cp.problem. You should have the objective and the constraints. Constraints I've already created here. I've combined the constraints. Then solution is equal to problem, because this has the complete formulation. Dot solve, open and close a bracket. Print the solution and print the values. So we run it. Here is a result. Here is a result at the bottom. But then this is all in one column. Very, very difficult to make out. So what I do is I reshape it. I create a new file called result and say np.reshape using the x value. There are two outputs here. One is a solution, which you get at the bottom. This is the least cost, 32,373. And the x value is the result. It's a result that we got in that. You may remember, it's a result we got in this, one of the earlier linear programming problems. The result. This formulation. So to bring it back into that formulation, what I do is I reshape it. I say np.reshape x values of the x value. I want 15 rows and 13 columns. I want 15 rows and 30 columns. 30 columns. And it should be in like this. It should be in continuous. It should be continuous. So just see what I do. I run it. I get the result. The result is now a matrix 15 into 30. And this what I do. I read it into Excel. I convert it into a CSV file. I'll first convert it into a data frame. I'll say result is equal to pd.dataframe result. And this result, I will write to a file called result2 and .csv. So here what I do is I first convert this result file into a data frame by saying pd.dataframe result, same result, and say result.to underscore csv result2. Or I can even call it output. I can also call it output. Sorry, I'll keep it all lowercase because it's very case sensitive. And if I forget, I may get into some kind of confusion. Okay, so I'm going to create a file called output, which is going to be in CSV format, which I can then easily understand. So I run it. And this output file will reside in this folder, which I created at the very bottom top. This folder. So I'll go to that folder and get that file called output. I'll change the name. So I'll go to that folder. It's in 122. And there's a file called output. Here it is. Here is my result, right? So I may need some more information. One is I will go to this KMF union and get the column titles from this formulation. I'll get the column titles. They're nothing but these. Okay, copy. Okay, get the column titles. And I'll get the row names also, which is also different, because row relates to the processing units. Control C. Okay. We have supply don't require. And my linear programming is solved. I'll make it into a number because these are scientific. So I'll go to number and I'll make it 2 digits and I'll get it. This is my allocation. So now we know from this center will receive 849 units of milk from this area. It will receive 130 from this area, and that's it. Okay. Now I'll go back and get the demand and supply. I have the demand and supply here. So just to check whether it's working or not, I copy this. All right. Since there's a formula, I'll just do it. I'll put it like a space special, right? And for the row, I should get the row total, the capacities. The capacities of the various plants that we are considering. So we'll copy that and put that at the end. Okay. And check whether this is right or not. So these are the actuals. And I want to check whether these add up. Okay, so this is how linear programming is done when you're working it practically. Look, the numbers are same. So it's working. The big problem, so I leave it to you to figure it out. Look, everything is identical. You can see there's no difference. Similarly, for here also, I'll do sum. So this is a very effective way of solving big linear program. Not very difficult. You may imagine it's very difficult. It's not. Okay. I'll do it again. Going back to that. Let's close that out. That's creating a problem. Equal to sum. And the linear programming problem. it's been solved. So this way, when you use Python, you from this interpretation very easy. Bangalore Milk Union will get milk from Bangalore urban and Bangalore rural. So that the minimum. Belgavi gets 730, 73 liters, units of milk from Belgavi itself. And there is an excess supply of milk of 926, which can use for private dairies. Now, this is cooperative dairies. They can use it for the private sector. So when the transportation problems become large, you must be in a position to access programs like Python, where it's rather easy to do that. This exercise was meant only to demonstrate how a linear programming problem, whether it's a transportation problem or a conventional linear programming problem, how they are to be solved in Excel. Okay, sorry, in Python. So then there is no limit on the size of the problems that you can handle. So only all they can be formulated in Excel and then brought to Python and then run in Python, and the results can be very easily obtained. And you can see it's just 3-4 lines. So with constant use, you can master it. Okay, so that is the purpose of this exercise was that, and with that I will conclude. And this is how large scale transportation problems are solved using Python. Thank you.